Welcome to 6502 Assembly Language Programming. In this video, we'll look at logic operations and conditional branches. The 6502 provides three varieties of logic operations. The first is AND this category includes the AND and the bit instructions. The next is inclusive OR. This includes the OR-A instruction, and the exclusive OR, which includes the EOR instruction. The 6502 AND instruction performs a bit-by-bit operation on two 8-bit values. For each bit, if both bits are a binary 1, the result will be 1. However, if either bit is 0, the result is 0. This sets the Z flag in the PSR if all the bits are 0. In other words, if the result is 0. Otherwise, it would set Z to 0. And it sets the N flag in the PSR to 1 if bit 7 of the result is 1. Otherwise, it sets N to 0. Here we show an AND operation example. In this example, the A register contains this value here, which I won't read in binary, but would be 52 in hexadecimal. The next entry is the operand, and the final entry or row in the table is the result. Now, as you can see, if both bits are 0, you get 0. If only one bit is 0, you still get 0. It's only in the case where you have both bits to 1 that you get 1. So the result of the operation would be this, which would be hexadecimal 02. I need to mention the 6502 bit instruction, which behaves very similarly to the AND instruction, except that it does not return a result. The only changes it makes are to the PSR flags. The 6502 OR-A instruction performs an inclusive OR on two 8-bit values. For each bit, if either bit is a binary 1, the result will be 1. However, if both bits are 0, then the result is 0. This operation sets the Z flag in the PSR to 1 if all the bits are 0. Otherwise, the Z flag is cleared. And this operation sets the N flag in the PSR to 1 if bit 7 is 1. Otherwise, N is set to 0. Here is an OR-A example. This entry in the table, this row, shows what's in the A register. This row shows the operand. Could be in memory or it could be immediate. But as you can see, if either bit is 1, the result is 1. And this particular operation would set the Z flag to 0 and the N flag to 0. Z flag to 0 because the result is not 0. There are lots of 1 bits. And the N flag to 0 because the 7th bit is 0. The 6502 EOR instruction performs an exclusive OR operation on two 8-bit values. For each bit, if the bits are equal, then the result is 0. If the bits are different, however, the result will be 1. And this operation sets the Z flag and the N flag in the same manner as the AND and inclusive OR operations. In this slide, we look at the exclusive OR operation. The value in the A register is depicted here. Here's the operand, and here is the result. As you can see, if the bits are the same between the A register and the operand, the result is 0. But if the bits are different, the result is 1. Different means 0, or I'm sorry, the same means 0, different means 1. Here they're different, here they're different, here they're the same, giving a 0, and finally these two are different, giving a 1. And exclusive OR sets the Z flag and the N flag in the same manner as the other operations. Let's talk about conditional branching. The basic concept is that you don't want to execute the same code in every instance. For instance, if you're calculating a grocery bill, you'd only want to run the add tax code for items that are taxable. If an item was not taxable, you'd want to skip that code. This slide presents the 6502 conditional branch instructions. As you can see, the table is organized in such a way that the instructions are presented in pairs. For instance, the branch of carry clear, BCC, and branch of carry set, BCS instructions both interrogate the carry flag, and they are grouped together. Whereas BNE, branch of not equal, BEQ, branch of equal, interrogate the 0 flag, Z flag, and so on. So the main point is that these instructions interrogate a certain flag in the PSR and take a branch or don't based on the value in that flag. So I hope you've been able to absorb this. Let's go to the IDE and see this in action. Let's take a look at logic operations and conditional branches in the 6502. Now I do want to mention, if you find any of this confusing, if you're not familiar with how this website works, do check out the previous videos. You'll find links in the description. We're looking at ex3.asm in the 8 bits and 1 byte website. And let's have a look at how to satisfy the requirements of this exercise. It features 3 parameters labeled param0, param1, and param2. Param0 is a bit pattern that tells you what to do with the other parameters. In particular, bit 001, 0000 being on means to add param1 and param2. But if that bit is off, then we want to subtract param2 from param1. That same parameter contains another bit that will indicate that you should negate the answer that you obtained from doing either the add or the subtract. You'll want to store the final result in output 0. So I'm not going to make you watch me code the solution to this one. It's a little bit longer than the others, but I'm going to click the See Solution button and load the solution I've coded previously. Now would be a good time, if you want to pause and have a go at the solution yourself. Well, good luck. And welcome back. So let's load up my previously coded solution. And then click the Run tab and start stepping through it. I'm scrolling down to EX3. Here it is, putting a breakpoint there. So what I'm doing here is I'm loading up param0 and then testing the bit we talked about, and then issuing a conditional branch based on that test. So we've loaded param 0. Clicking on the CPU tab, we see that it has 2 bits set. Testing one of them here with the AND. The result is not 0. This bit is on. And so the 0 flag over here is set to 0. That means this branch will not be taken and will add the 2 parameters. You always have to clear carry before performing an add, unless you're carrying over information from a previous add. That's not our design here, so we'll clear it. We're loading param 1, adding param 2, and now we're going to do an unconditional branch called a jump to the code where we're going to see if we need to negate it. Before testing the negate possibility, we need to store our preliminary results. Now we'll load up param 0 and test this other bit. And as you can see, looking in the CPU tab, that bit is on as well. So we're going to negate the value that's in the A register. I'm doing it here slightly complicated. I'm doing the negation in a slightly complicated way because I want to show off some of the instructions of the 6502. There is a simpler way to do this, but for now we'll continue with this method. We're going to load up the provisional result. That was an output 0. We're going to issue an exclusive OR against hexadecimal FF, and this will invert. Doing an exclusive OR against the value that's all ones will invert the original value. So looking at the register here and then doing this step over, you'll see all the bits have been inverted. Now we're going to do an add. And so we're clearing the carry beforehand and doing an add. Now this process of inverting all the bits and then adding 1 is how you negate a number in a 2's complement machine. We could have done it in a simpler way just by loading a 0 into the A register and subtracting output 0. That would have been a lot simpler, but I did want to show this technique, and I did want to show off the exclusive OR instruction. So having done that, we're storing the result, and then this instruction, implemented in the X register, tells the test framework that it should examine our output. So we're going to clear our breakpoint. Click resume, and you see that we passed our 4th exercise. The test framework likes it. Okay, well that concludes this video. I hope you derive some benefit from it. If you have any questions, please put them in the comments below. I would also appreciate a like and subscribe if you enjoyed this video and derived benefit from it. Thank you very much and have a great day.